Okay, today we're talking about Chapter 3, Section 1, Quadratic Functions. So you've seen or heard of quadratic functions for quite a while now. They are used very extensively in this course, obviously, in pre-cal and even in calculus, mainly because they are they're pretty easy to work with. There's multiple ways to find solutions. There's many ways to work on quadratic equations. And so let's look at what a quadratic equation looks like graphically. Just a couple of generic equations here. Alrighty, so a couple of generic equations. If we have, here's my laser. All right, if we have some parabola. It's a quadratic equation, right? It's ax squared plus bx plus c, where we have a is greater than 0. So this is saying that my leading coefficient is positive. If we have a positive quadratic equation, then we have a parabola that opens upward. Okay, if we cut it right down the middle, we call that the axis of symmetry. And this point right here, where it changes from going down to going up, the slope from going down to going up, we call that the vertex. All right, and I mean essentially the same if we have a parabola opening downward, right? The very middle, we call that the axis of symmetry, but this time it's the very tippy top, the maximum point there, where we change from going up to down, we call that the maximum. All right, so graphing a quadratic equation, something that's super easy to do, first off, is if we have a quadratic equation in what's called the vertex form. Okay, so if we have a graph that's in the vertex form, the quadratic function, f of x is equal to a times x minus h quantity squared plus k, where a is not equal to 0. Of course, if a is equal to 0, it would make that entire term 0, right? And it would just be k, so that's why a cannot be equal to 0. This is called vertex form. The graph of f is a parabola whose vertex is the point hk. Okay, so notice how the vertex is essentially the opposite sign of whatever this h is, right? In the formula, it's a minus h. The vertex is at h. So keep that in mind when we see that here in a moment. And then plus k, so then well, k is k, right? The parabola is symmetric with respect to the line x equals h. So we're saying that my line of symmetry, or my axis of symmetry, is x is equal to h. And if a is greater than 0, the parabola opens upward. If a is less than 0, the parabola opens downward. And of course, we saw that here. Right? All right, so graphing quadratic functions with equations in vertex form. So what we're going to do is we're going to look at these equations. We're going to figure out all the characteristics of the equation, then we're going to graph it. And then for this, I'm going to do a rough graph, and then I'm going to snip the prettier graph, right? The one that the textbook has. But anyways, what we're going to do is we're going to determine whether the parabola opens upward or downward. That's pretty easy, right? If it's positive or negative. We're going to determine the vertex, which is going to be hk. We're going to find any x-intercepts, find any y-intercepts, and then we're going to plot the intercepts and the vertex, and we're going to connect these dots, and we will have our equation. Okay, so let's go ahead and do example 1 here. Alrighty, so if I'm going to graph this equation, I need to know a couple of things. Okay, first thing I'm going to do is I'm going to note. Hang on, it's not working. Of course it wouldn't. Right, there we go. Okay, so the first thing we're going to do is we're going to note if it opens up or down. Okay, let's see. How would we 1, 2, 3, 4? Okay, so I'm just going to go. Well, I don't know if y'all can see that, but I'm just going to go according to this. Okay, 1, 2, 3, 4, 5. Now, 1 is, do we open upward or downward? So looking at this graph, it is a -2. Okay, so since it is a -2, this tells us that we're going to be opening downward. Okay, so down. The second step is we're going to find the vertex. Now the vertex is simply just going to be not negative h. Sorry, it's just going to be hk. So it's going to be the opposite sign of that value there. And if it's a negative 3, I'm going to put a positive 3. And then the other part is going to just be that number there, and it's just 8. So positive 3, positive 8. Okay, and that's the vertex. Pretty easy stuff. Again, that's just following along with my my equation here. Again, my vertex 4 is x minus h, and my vertex is hk. So it's essentially the opposite sign of the h that you see in parentheses, and k. The opposite sign of negative 3 is a positive 3, and then k, which is 8. Okay. And then step 3, we need to find the x-intercepts. Yeah, 3 is x, 4 is y. Okay, so step 3, we're going to find the x-intercepts. So the x-intercepts, it's going to be wherever this equation is equal to 0. Okay, so what I'm going to do is I'm going to set the function equal to 0. So I'm going to say 0 is equal to negative 2 x minus 3 quantity squared plus 8. All right, solving for 0 here, sorry. What we're going to do is we're going to subtract 8 from both sides. So we're going to have a negative 8 is equal to a negative 2 times x minus 3 quantity squared. We're going to multiply, we're going to divide both sides by negative 2. So it's going to become a positive 4 x minus 3 quantity squared. We're going to take the square root of both sides. So by taking the square root of both sides, we're going to have plus or minus the square root of 4, which is 2, is equal to x minus 3. And then let's go ahead and polish this off. Let's put it in green to really denote the difference there. It's just going to be, we're going to put the x on the left side. It's going to be, we add 3 to both sides, so x is going to be equal to 5. And then we add a 3 to a negative 1. We're going to have a, or I'm sorry, negative 2. We're going to have a positive 1. Okay, so my x-intercepts are at 5 and 1. Okay, so let's move on to the y-intercept. Now the y-intercept is super easy. Let's see, let's snip this, put it on the next page. Okay, so that was step 3. Yeah, and then we'll go to step 4. Like I said, the y-intercept is super easy because all we have to do is set x equal to 0, right? So step 4, the y-intercept. We're going to set y equal to 0, or I'm sorry, x equal to 0. And so we'll have a negative 2. Now let's just go ahead and put 0. Let's just go ahead and make this, or write this out just in case it gets a little confusing. No mental math. Okay. And then it's equal to, well, we have a negative 3 squared, which is 9. 9 times a, well, negative 3 times negative 3 is positive 9. A positive 9 times negative 2 is a negative 18. Plus 8, which is just going to be equal to a negative 10. And let's put that in green as well, actually. Okay. So my y-intercept is at negative 10. And so let's do this. Let's differentiate here. Okay, so my graph, if I have to go to negative 10, my x-intercepts, 5, 1, okay. So it looks like I just need to do really want to make this look nice. That should be alright. Okay, so we have a negative 1, 2, 3, 4, 5, 6, 7, and that's not nearly enough. Okay, so this is just the bottom part of a graph. Let's try this again. Okay, so that's good. All right, so that's negative 11 going down on the y-axis, and then okay, so there we go. So let's go ahead and plot everything we know so far, okay? So my vertex, oh no, it's at positive 3, 8. Okay, I'm just gonna go ahead and snip this graph because it's kind of large um, for me to graph it here. But as I'll describe it. Okay, no big deal, no big deal. Okay, so that is a big deal because that shouldn't be there on that page. Hmm, there's a lot of silence there. Okay, so let's go back to what we're talking about. Okay, so we have the vertex is at positive 3, positive 8. And so we'll go over here and we plot this point here, positive 3, positive 8. Okay. The next thing we have are our x-intercepts, which are at positive 5 and positive 1. So what we would do is we'd go over here and we would plot points at positive 5, positive 1. And then the y-intercept's at negative 10, so we go down 10 on the y-axis, like so. And you know, let's just imagine that blue line isn't there, right? And so what we would do is we would just look at the red line, the red dots we have here, the dots being the vertex and the x and y axis, and we would just connect the dots, like so. And of course that goes to, you know, leads to number one, which is saying that we have a parabola that opens downward. But anyways, yeah, sorry about that. I mean, maybe that's just the way to go instead of just trying to graph it. Um, I think that's okay. Okay. Well, that's example one. We're 12 minutes in, and that's example one. All right. So example two. Oh no, things just aren't working out today, are they? All right. So the first thing we need to do, you know, we ask ourselves, does this open up or does it open down? Well, I mean, it has a positive leading coefficient, so we would say that we open up. B, my vertex is at, looks like again, it's the negative of whatever sign, whatever number's in there. So that's a positive 3, so we're going to make it a negative 3. Negative 3, and then positive 1. And then we look for the x intercepts. So C, the x intercepts. We're going to just solve this for 0. So we got 0 is equal to x plus 3 quantity squared plus 1. All right, so we're going to subtract 1 from both sides. So we've got a negative 1 is equal to x plus 3 quantity squared. And then if we take the square root of both sides, okay, we're going to take plus or minus the square root of negative 1. That's equal to x plus 3. Now, for all intents and purposes, we are officially done with trying to find the x-intercepts. Why? Because we can obviously proceed, and let's just go and proceed just to kind of show you, I guess. My x-intercept is going to be equal to, if I subtract 3 from both sides, it's going to be equal to negative 3 plus or minus I. Okay? So whenever you see this, you can pretty much be done with finding x-intercepts, and here's why. Have any of you ever plotted, and you might have, okay, so I don't know, maybe it's not the right question, but in our college algebra course, we don't plot imaginary numbers. Now you can on an imaginary plane, but for this course, we don't know how to plot imaginary numbers. So there are no x-intercepts. Okay, so if you get an imaginary number, you can pretty much stop there. Okay, so there are no x-intercepts because we cannot plot that on the graph. On the previous example, we had x-intercepts that we were able to plot, right? We plotted them at 5 and 1, and that's what we saw over here at 5 and 1. We can't do that with imaginary numbers though. Okay. And D rather. Oh, I didn't mean to put D. I meant to label them 1, 2, 3, 4. Let's go. Let's fix that real quick. Okay. Um, and then my y intercepts. Well, again, I set x equal to 0, so I'm going to have um, 0 plus 3 is 3. 3 squared is 9. 9 plus 1 is 10. So y equals 10 is going to be my y intercept. Let's go ahead and snip this. Alrighty. So starting with the vertex, it's at -3, +1. You go left 3, up 1. We have that point right there. The x-intercepts, again, we don't have x-intercepts, right? We will not cross the x-axis at no point because we have imaginary numbers, and of course that's reflected on the graph. Notice how, I mean, since this is a parabola opening upward, notice how we don't cross the x-axis here. So that makes sense now, doesn't it? Okay. And then y equals 10 is my y-intercept, which we plot here. And again, imagine the blue line isn't there. We only have 2 points. But since we know that it is a parabola that opens upward, and the vertex is at -3, +1, we can essentially take that point and draw an upward parabola. And that is how we can graph that function. Okay. Alrighty, so it is pretty darn convenient that we can have our quadratic equation. Let's go back here. It's pretty. Oh no, that's not it. Well, let's amend this a little bit. Oh, it does say it actually. Yeah. Okay. But I'm still gonna write it. So we know quadratic functions are functions in the form ax squared plus bx plus c. Okay. We know that's our quadratic equations, and so far it's been pretty darn convenient that our quadratic equations, are in vertex form. And being in vertex form makes it really easy to find the vertex, right? But what if you had an equation that looks like this? How do you find that vertex, right? So let's go ahead and talk about that. So, algebraically, and I mean, if you care, you care. If you don't, you don't. I understand, but I mean, it's not really that important. I don't think, not for this course, anyways. If we have our quadratic equation, all right, if we factor out an a and complete the square, we can create an equation that is in vertex form. So, what that page is basically saying is this. Okay, so lucky for you, you don't have to freak out if you have an equation in the form of ax squared plus bx plus c to find the vertex. Okay. Now, obviously, if something is an ax squared plus bx plus c, our normal quadratic equation, the only thing that's different, essentially, right? We can tell if it's opening upward or downward. We know how to find the x-intercepts. We know how to find the y-intercepts, and of course, we know how to plot plot the points. The only difference is that the vertex is going to be a little bit harder to find. I mean, by a little bit harder, I mean like 20 seconds longer, right? It's not going to be just as easy as looking for h and k. Instead, we're going to do just a little bit of algebra, and that algebra is basically saying negative b over 2a and the function negative b over 2a. So real quick, let me explain something that you already know, but maybe just seeing it a different way would help. Okay, so when we plot points, we plot points x, y. Okay. Well, another way to think about x, y is x and f of x, right? If we were to plot points on a graph, they're essentially the same thing, saying x and then f of x. Okay, so for instance, an example would be, if we're trying to plot a point, well, we would plot the point 3 and then the plot f of 3 by plugging in 3 into your function. So that's essentially what we're doing over here. All right, our x value is going to be negative b over 2a. Our y value is going to be the function at negative b over 2a. Okay, so you don't actually have to write negative b over 2a for the y value. You just basically plug in whatever x you have into the function, and you'll get your y value out. Okay, and that's the only difference. Again, step 2 is the only difference. Step 1, we can tell if it's open up or down. We can know how to do x-intercepts. Y-intercepts are even easier in our quadratic form, and of course we plot the points. Now, of course, these are all words. Let's look at an example. Alrighty, so step 1, are we opening up or down? There's a negative in front of the x squared, so we are going to be opening down. Step 2, again, there's just a slight difference, a little bit hard, like 20 seconds longer, if that. Well, maybe 25. All right, so what we're going to do is we're going to figure out negative b over 2a. Okay, so let's write that down. So we're looking for the x value, so that's going to be negative. Let's change that. Yeah, so negative b over 2a, that's equal to a negative. What is my b value in this equation? Well, it is a negative 2, right? It's in the b section. And so let's go back and talk about that for a hot second here. Looking at this, the a is my leading coefficient in front of the x squared. The b is my term in front of the x, and the c is my constant. Okay, so a is the very first number, b is the second number, and c is the very last number, which does not even have a variable attached. Okay, so negative, and then b, well, b is going to be a negative 2, and it's important you write that because it can be very complicated. It can get very sticky very fast, and honestly, this is a really good example of it. Okay, so we have negative 2 for a b, and then 2 times a. Well, what is a in this particular case? Well, it's going to be a negative 1. Right? A negative 1 is in front of the x squared. Okay, so again, we've got 3 negatives here, and that's why it's important to keep track of your negatives by actually writing them out. Okay, so we're going to have a negative 2 over, well, 2 times a negative 1 is a negative 2. All right, so a negative 2 divided by negative 2 is a positive 1, and then we still have this negative sign here. So it would be a negative 1. So negative 1. Okay, this is the x value of my vertex. To find my y value, I just plug the negative 1 in. Okay, so let's put, this is the x value. That's horrible, Sherman, horrible. There, the x value. Okay. Now to find the y value, again, what I'm going to do is I'm going to take the equation, and I'm going to go ahead and let's change it from green to something else. I like to save green for a final solution. Let's change it to blue. Okay, that is the x value. All right, so here we go. So f of negative 1. Oh, didn't even make it blue. And again, I'm just writing the equation here. Okay, so we have negative, and then x squared. So we're going to say negative 1 squared minus 2 times a negative 1 plus 1. Okay, so doing the arithmetic here, negative 1 squared is a positive 1. The negative in front makes it a negative 1. Negative 2 times negative 1 is a positive 2 plus 1. So we got 3 minus 1, so it's a 2. Whew, okay, so this is my y value. Okay, so my vertex is going to end up being a -1, +2. All right, hopefully that made sense. All you do, you mainly just use a -b over 2a to find the x, and that's what we did here. Once you find the x, you plug it into your function, and then you find the y. And then those two together give you your vertex, right? And there's your daily dose of John Madden there. So that's the vertex. Now let's find the x-axis, or the x-intercept and y-intercepts. So let's snip this and put it on the next page. The y-intercepts are super easy to find, aren't they? But let's stay in order here, and we'll do the x-intercepts first. So 3. My x-intercepts I'm going to take this equation, solve for 0. So I'm going to have a negative x squared minus 2x plus 1 is equal to 0. And I'll be honest, I can't factor this in my head in 3 to 5 seconds, so I'm going to have to go to the quadratic formula. Okay, and if you've forgotten the quadratic formula, it is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so let's proceed. Here we're going to have x is equal to, all right, so it's going to be a negative b, so negative, and then b is a -2, so negative, -2, and again, be very cautious with your negative signs there. Plus or minus b squared, so it'll be a -2 quantity squared minus 4 times a times c, so 4 times a, which is a -1, times c, which is a +1, all over 2 times a, which is a -1. Okay, so this turns into -2 is a +2, plus or minus. -2 squared is a 4. 4 and then -1 is a +4, so 4 minus a -4 is going to be 8, so 4 or 2 plus or minus square root of 8 all over -2. And if we put that into the calculator, we end up with x is equal to a -2.4 and a 0.4. Okay, and that's more or less an approximation actually. So we put squiggly equal signs. So my x-intercepts are at -2, -2.4, and at 0.4. Okay, and then I mentioned like 10 minutes ago, it seems like, the y-intercept is so easy, and it's because it's just basically the constant, right? Because, let's say this is step 4, the y-intercept, I set x equal to 0, right? Well, if I set x equal to 0, this x goes to 0, or that's 0, and we just end up with a 1. So my y-intercept is at 0, 1. Okay, and let's graph this. That's interesting. Which one of these do I want to graph? Nah, we'll just do this one. All right, so again, kind of everything, the same thing we've done with the entire lecture so far. Let's go back. We know we open downward. My vertex is at -1, +2. So we would plot the point right here at -1. Well, that's -1, +2. We have the x-intercepts at approximately 0.4 and -2.4. So, you know, close to the halves, right? So -2.4 and 0.4. And we are opening downward. We have the y-intercept at 0, 1. So We do that, and then of course we connect those dots. Okay. Whew. Alrighty. So next up, we're going to be talking about maximum and minimum values. All right. This is a pretty easy concept, and luckily, you know, we need a nice little break every now and then, right? And this is our break for this section. So maximum and minimum values of quadratic function. So if we consider the quadratic function, if a is greater than 0, okay, so let's go back looking at a. A is the leading coefficient. Well, it's the same problem, but yeah, the leading coefficient every single time. It's the leading coefficient. Okay. So basically, how we determine if a parabola opened up or down. If a is greater than 0, then we're going to have a minimum value at the vertex. If a is greater than 0, let's underline these two. If a is greater than 0, then we're going to have a maximum value at the vertex. And that's it, right? If we're opening up, well, then there's going to be a value right here that is a minimum. If we are opening down, then there's going to be a value right here that is going to be a maximum. And that's the concept, guys. The vertex can be a minimum or a maximum depending on if we're opening up or down. So, let's do example 4. Alrighty, so A reads, determine without graphing whether the function has a minimum value or a maximum value. Okay, so looking at the function, it's a negative 3x squared. So if it's a negative 3, we know that it is a parabola that opens downward. Okay, and if it's a parabola that opens downward, then it must have a maximum, right? Because, well, it's opening downward. There has to be a maximum there. And you know, that's actually a pretty good idea. So let's go ahead and do this. Move it over here and denote this as A, and we'll say a maximum. Okay. Alrighty. Next up, we're gonna find out what it is. Right. B reads, find the minimum or maximum value. All right. Well, this is a max, so we're gonna find the maximum value. So what is the maximum value? Well, that's just gonna be the vertex. Well, unfortunately, we're not in vertex form. We are in our normal quadratic form, so we're gonna have to do the negative b over 2a. So negative b over 2a, and then, well, let's do this actually. Negative b over 2a, and then the function at negative b over 2a, whatever it may be. Okay. So what is negative b over 2a? Let's work it out over here to the right. It's going to be a negative b, which is 6, over 2a, so 2 times a negative 3. Okay. So we got a negative 6. 2 times negative 3 is a negative 6. Okay. And then we have a negative 6 over a negative 6. So it's going to be a negative 1, which is going to be positive 1. So my f, or my x value is a positive 1. And then we're going to figure out what my function is at 1. Okay. Well, we're just going to do f of 1, which is going to be negative 3 times 1 squared plus 6 times 1 minus 13. So we've got negative 3, 1 squared is 1, plus 6 minus 13. So negative 6, so we have a negative 10. So negative 10. And you know, let's actually change that to positive 1, negative 10, like so. Okay, and that is the vertex. That is the maximum value. C reads, identify the function's domain and range. Well, guys, this is a quadratic equation. If you recall with my domain Bible we talked about a few sections ago, every equation's domain is negative infinity to positive infinity, unless we have those two stipulations, right? If we have a variable in the denominator, or if we have a variable in an even indexed root. Well, this is a quadratic function. All quadratic functions have domains from negative infinity to positive infinity. This ain't working like I wanted it. There we go. And the range, well, the range is going to be dependent on our vertex, okay? So if we have a vertex and it has a maximum at, this is essentially going to be, right, the vertex, which we figured out in B was 1, 1, -10, all right? Well, then that means that every value in this particular every value in the range here is going to be from -infinity up to a -10. Okay, so my domain is, or I'm sorry, my range is going to be from -infinity. That's a horrible infinity to -10, and then we include -10 because that's we're actually going up to it. Okay. All right, so the last two or three problems I think are going to be nice, long word problems. Finding minimums and maximum values. All right, so these word problems are going to be problems that you kind of have to think through, okay? And I have my own personal opinion on these word problems, and I'm just going to share it with you because you are in my class, and if you don't like it, you can fast forward it, right? So many times students are like, what does this have to do with the real world? I can't use this in the real world. Well, whenever we start to get to problems that we do use in the real world, maybe not so much this one, but definitely the next one. Whenever we get to actual problems we do use in the real world, people's brains shut off and say, I can't do that. And it kind of bothers me because it's like you're eating your cake and having it too. You're saying you don't teach me that, and then when we do, you're like, nope, not doing it. So that's kind of my spiel on word problems, but I digress. Anyways, um, a lot of these you kind of have to think through, and you got to make sense of them on your own. But I can obviously do a couple of them. So example 6, among all pairs of numbers whose difference is 10. Okay, so what does that mean? Pairs of numbers whose difference is 10. I mean, it could be -100 and a positive 110. Right? Their difference is 10. And there's obviously an infinite amount of these, right? Because you can say -1 million and positive 1,000,010. So that's what that's what that's saying. Find a pair whose product is as small as possible. So we're looking for the smallest number possible, whose product is as small as possible, right? Something like you know, well, that's not zero. When I said 100 and or -100 and positive 110, right? If I multiply those two numbers together, that's going to be smaller than my example of a million, right? So we're trying to find uh, two numbers whose difference is 10 and their product is the smallest available product. Okay. So the first thing we're going to do is we're going to say, all right, among all pairs of numbers whose difference is 10. So x minus y, doesn't matter what x is, doesn't matter what y is, its difference is going to be a positive 10. Okay, that's one thing. And then secondly, most importantly, their product is as small as possible. All right, so that saying it wants that as small as possible, it's telling us we're looking for a minimum. Right? And luckily, we're in a section talking about maximums and minimums, right? Alrighty, so what we're going to do, notice how in both equations, and you've done, I'm sure you have similar examples like this. In both of these equations, we have two variables. So what we're going to do is we're going to have to make a substitution from one equation into the next. Okay, so what is that substitution going to be? Well, the easy substitution here, let's just substitute in for y. Okay, so let's take this equation, solve for y, and if I solve for y, I end up with a negative y is equal to a negative x plus 10. Well, that's not 10, plus 10. And if I multiply both sides by a -1, I would end up with y is equal to an x minus 10. Okay, so what I'm going to do is I'm going to take this y value and I'm going to plug it into this y value. The reason why is because now I will no longer have an x. Okay, so by plugging into that y value, and let's go ahead and I don't know how I should color coordinate this. We have p is equal to x, and then it's times x minus 10. Okay, so notice what I did. So now I have an equation that only has one variable, and now I can work with minimums and maximums. Okay, so hopefully you see that. If by taking this equation and go ahead and distributing the x, I have x squared minus 10x. And notice how now I have a quadratic equation, right? Now it's a quadratic equation. It is a parabola that opens up, right? Because it's a positive x squared. So it's a parabola that opens up, which means we have a minimum, which is perfect because that's what we're looking for, a minimum value there. Okay, so what we're going to do is we're going to take this equation and we're going to find out what the vertex is, find out what the minimum is. Okay, and let's actually keep that there. All right, so it's going to be, all right, so my vertex is going to be negative b over 2a, and then the function at negative b over 2a. Let's fix that up a little bit. Okay, so what is negative b over 2a? I'm gonna do the arithmetic up in here and then put the solution down there. Okay, then let's put it in green. Okay, so a negative b over 2a, so negative b, which is a negative 10, over 2a, which is 2 times 1. Well, let's make that that. All right, so we have a negative 10 over 2. So we have a negative 5, which is going to be a positive 5. Okay, so the x value of my vertex is going to be a positive 5. What is my y value going to be? Well, I just have to plug in the positive 5 into my function here and figure out the y value. We can do this in our head. 5 squared minus 5 squared is 25 minus 50, so that's going to be a negative 25. Sorry about that. Let's see. Okay, I'll take that back because we're wanting to find the x value. So yeah, sorry about that. I don't suppose I necessarily need the vertex, but you know what? Let's actually put that there. Okay, 25. Okay, so my vertex is at 5, negative 25, but we are concerned with the x value here. Okay, and the x value here is a 5. All right. Well, that's my x value, and if you remember, I use the equation p is equal to xy, okay? But we need to figure out what y is. Well, how do we figure out what y is? We plug this x back into my original difference there, okay? 5 minus what is equal to 10? Okay, well, it would be 5 minus a negative 5, right? Minus negative 5 is going to be a positive 5, so 5 plus 5 is 10. So the pair of numbers whose difference is 10 is going to be 5 and negative 5. And that is the smallest number whose difference is 10 and who has the smallest product or the minimum product. Okay. Now, I feel like I might not have explained that fully, so I'm going to give it one more shot here. And it's from where we started. Okay. So we're going to have two equations. You're not, for this example and the next example, we're going to have that. But especially in something like calculus, you're going to have equations like this quite often, right? But anyways, we had two equations. We need to find a number whose difference, right, so a subtraction sign, whose difference is 10, and whose product is as small as possible. So what we did is we solved one equation for y and plugged it into the next equation. That way we had this equation here with just x's, right? Because obviously we can deal with equations with just one variable. All right, we distribute the x through, we ended up with x squared minus 10x, which was our quadratic equation. And from that, we found the minimum of that quadratic equation. And of course, I mean, it didn't just happen to be a minimum because the problem asked for it. It's a minimum because, well, the algebra behind it gets me a minimum, right? Because this is a positive x squared, which means that it's a parabola opening upward, which has a minimum. All right, well, the x value of that minimum is located at positive 5. So this is the x value, and now we can essentially put that right back into our original equation, or not original equation, but one of our original equations, and we had 5. Well, 5 minus what is equal to a positive 10? Well, that would be 5 minus a negative 5, right? Because that's essentially saying 5 plus 5. So that is the solution to my problem. My x value is 5, my y value is negative 5, and their product is negative 25, which is the smallest number you can have. Right, now, we'll say this is seemingly a number theory problem. The next example is going to be more or less in line with what you probably are used to. Number theory is fun, though. Okay, so it's kind of the same thing. Like, so we're going to have to come up with two separate equations here. All right, so let's read the problem. You have 100 yards of fencing to enclose a rectangular region. Find the dimension of the rectangle that maximize the enclosed area. What is the maximum area? Alrighty. Well, if I have 100 yards of fencing, so let's do a thought experiment here. We have a rectangle. Okay. This side is x. This side is y. Okay. Well, if that side x, that side is y, then does it not also make sense that this side is the same length as the opposite side? So this side is also x, and same can be said for this. That side is y. Okay. So I just got my perimeter. Okay. So my perimeter is going to be 2 times x plus 2 times y, and that's going to be equal to 100 yards of fencing, so 100. Okay. So there's that. Now, something else we also have to remember is my area. Well, what is my area? Well, my area is the inside of this triangle. It's just simply length times width. So it's just simply x times y. Okay, so we have the same kind of process that we did on the previous example. We're gonna have two equations. Okay, and similar to the previous example, we're gonna take one equation, solve it for y, and plug it into the other. So let's go ahead and do that. With this one, we subtract 2x divided by 2, so we're gonna end up with a y is equal to 50 minus x. Okay, and then we're going to plug that into our area equation. So now my area is going to be x is equal to, or I'm sorry, a is equal to x, and we're plugging this y value in for this y. So we're going to have 50 minus x. Okay, and the color was, all right, I made it blue. So if I distributed that x through, I would end up with a 50x minus x squared. And if we put it in descending order, we've got negative x squared. Now I probably should put in descending order to begin with. Negative x squared plus 50x. Okay, so looking at this equation, well, cut off the negative. Looking at this equation, we see that it is a parabola and it opens down, right? It's a parabola that opens down, and therefore we're going to have a maximum, which again isn't a coincidence that we are looking for the maximum area for this particular problem, right? That's just how math works. So how do we find the maximum? Well, again, we find the vertex. Okay, so my vertex is going to be negative b over 2a. So again, let's do it like this: negative b over 2a, and then f of negative b over 2a. Okay, and if we were to follow along with this, again, I'm going to do the arithmetic up here somewhere, and then just translate it down into down here. All right, so negative b over 2a, so we've got a negative, and then b, which is a 50, over 2a, which is 2 times a negative 2 times a negative 1. So end up with a negative 50 over a negative 2. So we have a negative 25. A negative negative 25 is a positive 25. So that is the x value of our vertex, so 25. I don't think we need the y value, but let's just go ahead and get the y value anyways. Okay, so the y value is going to be, if we plug in a 25 in for x here, and I'm going to have to put a calculator out for this one. Unfortunately, I don't know, it's just a long day. Oh yeah, 625, that's what it is. Yeah. Well, it's 625, okay. So 625. And again, it's not necessarily needed for this problem, but I did it anyways. Okay. So we got our area. We got the coordinate of the maximum of our parabola. But we don't really, but it's not really that important. Instead, we're trying to figure out, what would my area need to be? Okay. Well, if x is equal to 25, and then plugging that 25 into this equation, right? 2 times 25 is 50. So let's run out of room here. All right, so bear with me here. Pay attention. Let's move this. Let's put it in green, kind of down here. Okay. So 2 times 25, because again that's my x value here. 2 times 25 plus 2 times y is equal to 100. Okay. Well, 2 times 25, that's just 50. It's just 50. And I'm trying to find my y value here. If I subtract 50 from both sides, I've got 2y is equal to 50. And then I divide both sides by y, I get y is equal to 25. So it appears y also needs to be 25. Okay, so what is the maximum area? Well, if x is 25, y is 25, 25 times 25, that is going to be 625. Okay, and again, that's the area. So we would say 25 times 25, which is equal to 625. And that is the maximum area. Whew, hopefully you followed along there. If you didn't, hit rewind. And I believe that concludes today's lecture.